Welcome back, Calculus. We'll be doing 4.8 more with connecting the graphs. And there's so much to write on this that I thought the best way to approach this problem would be to look at the answer key. So just pay close attention to the directions and what you can conclude about a graph. So as we're looking at this, we're given the graph of f, and the first thing that you could talk about is f prime of x, and the first thing that you might want to notice is the horizontal tangent lines. That's the very first thing that we talk about here. And the horizontal tangent lines would be at x equals -4, x equals -2, and x equals 1. You can talk about the reason why the derivative equals 0 is because we have relative extrema. Now be careful with this, because sometimes we have relative extrema where the derivative does not exist, but because this looks like a polynomial, I think you'd be safe with that reason. I don't always agree with the explanations perfectly, but that's pretty good. I'll stick with that. As you look at this problem, if we have 3 turning points, it doesn't have to be true, but a lot of times we can make this connection that this looks like a quartic. It's a 4th degree. It's got 3 zeros, but this one has a multiplicity of 2. You may remember that from pre-calculus, that when it bounces off the graph, it has a multiplicity of 2. Meaning that when you take the derivative of a quartic, you'll end up with a cubic. Now, I'd probably mention the third one first, which is when the derivative is positive. That means the function is increasing. I think it's pretty clear that it's increasing from -∞ to -4. Now, I would put a bracket here, but maybe the directions would say on what open interval is it increasing, and then you wouldn't have to think about bracket or parenthesis. So you're probably safe if you do either. But pay close attention to the directions as we get into more AP practice. I'm sure it'll say open interval. And then it's also increasing. F of x is increasing from -2 to 1. So that means the derivatives function is positive. Okay. Notice his reason is also about increasing. So when would the derivative be less than 0? It would be everywhere the function is decreasing. So from -4 to -2, and then 1 to infinity. What else do we know? Probably is safe to assume that because the function has an end behavior where they're both going down, then the derivative, I should rephrase it, the function must have a negative leading coefficient. So then the derivative must also have a negative leading coefficient. Think about the derivative of a leading coefficient being negative. It's still going to be negative as you look at a polynomial like that. Maybe another thing to mention would be that the derivative changes from negative to positive. It's negative to positive, positive to negative, things like that. It's all about mins and maxes. Man, I scrolled down way too fast there. You might be thinking the same thing. If you have a min for a function, that means that the derivative must go, has a negative slope to a positive slope. So that means the derivative changes from negative to positive. And then flip that for a maximum. So wherever the function has a maximum, then the derivative changes from positive to negative. And then 8, 9, 10, 11 talks about the about concavity, right? So the derivative has a relative min at x equals -3. That's approximate. I guess I should clarify there. And if anybody's confused by this, by the way, you can pause the video at any point. Just friendly reminder. It might actually be helpful if I were to graph those derivatives. So let's do that real quick. So maybe I'll do this in the color that we have. We have if you remember from my previous lesson, identify your mins and maxes. That's where the derivative is equal to 0. So I'm just putting zeros here. And if the function is increasing, that means that the derivative must be positive. So it's increasing here to here. So I'll just make a little loop like that. And then where the function's decreasing, I'll do a slightly different color, it must be below the x-axis. So from 1 to infinity, it's decreasing. I don't really like that I used two different colors there, so let's just stick with the same color. Oh, that was a terrible. So this would be f prime of x. And this could help you understand everything that was written on the previous problem. So then as we get to the second derivative, remember the second derivative is the derivative of the derivative. So maybe identify where those zeros are. And these are approximate. Okay, it's not necessarily the midpoint halfway between those zeros, but there it's about. And you can see that the first derivative, the orange thing that I drew, is decreasing, so that means the second derivative must be negative. And then it's increasing, the orange is increasing, so that means the second derivative, the green, must be positive. When orange is increasing, the green is positive. First derivative is increasing, the second derivative is positive. And then it's decreasing, so negative for the graph of the second derivative. So as I go back to the answer key, I think you can see, especially 10 and 11, how if f prime is increasing, that means that the second derivative is going to be positive. And he went ahead and used the midpoints. If anybody's curious where these x values come from, that's what he used. And then decreasing the same thing. And that actually answers the 4 conclusions that he wrote down about the second derivative. So if the second derivative is 0, that must be the point of inflection. And again, we're just approximating here at -3 and -1/2. That's the best thing we can do when we're given a graph, is approximate. And then from there, we can answer these questions where the second derivative is positive. Okay, and we could actually look at the graph. I think it's worthwhile to mention, looking at the graph, that you can see that the second derivative is positive. The function that they give you is concave up. And then the second derivative would be negative, where we have a concave down. So from negative infinity to -3, approximately -3, and then -1/2 to positive infinity. And by the way, intervals of concavity, we always use open intervals. I have not seen anybody use a closed on that one. That's not really up for discussion. And then, the same reason as before is if we took the derivative of a quartic, we get a cubic. Well, if we take the derivative of a cubic, we'll get a quadratic. Which is why all of our rules from pre-calculus have followed us. So I'm going to move on to the next problem. And I think I'll do what I just did, which is graph and then kind of talk about it. Now notice in this problem, though, they provide for you the derivative. That's what I meant earlier when I say pay close attention to this. Now the thing about going backwards to the graph of f is this graph could be shifted anywhere. All I know is that this point is an extrema, this point is an extrema, and this point is an extrema. And more specifically, those 3 points, well, this one, we're going from decreasing to increasing, because the first derivative is positive. So if you were to graph that, decreasing, again, I just picked a random point. I was trying to get it kind of out of the way. To increasing, it must be a minimum. And then this point going from increasing, because the first derivative is positive, to decreasing, it must be a maximum somewhere. And then right here, going from decreasing to increasing, because the first derivative is negative to positive, must be a minimum. And we'll worry about a little bit cooler stuff later. So again, you could shift this pink graph up and down wherever you want it, because, well, you'll learn it in the next, I think Unit 6 actually, where we get this plus a constant at the end. And think about it, if I asked you to take the derivative of a constant, you'll get 0. So that's why we get to shift up and down. And then the second thing I would point out is the potential graph of the second derivative. Now you don't really have any leeway with this because the min or max has to cross the x-axis. And the only way to go from increasing would be a positive second derivative, to decreasing would be a negative second derivative, to increasing would be a positive. That's a very lame graph, but there you go, f double prime of x. So now, once you have that identified, you could make conclusions about this problem. So we can go back to that answer key. So I don't like that it doesn't draw that out, but you can answer these questions. You don't need to draw it. So the fact that from negative infinity to negative 2, the derivative is below the x-axis, f prime of x is less than 0, that must mean that the function was decreasing. It's also below the x-axis from 1 to 3, so the function is decreasing. So what if the derivative is above the x-axis, the derivative is positive, then the function must be increasing. So what else do we know? Well, if we go from decreasing to increasing, it must be a minimum. So if we go from a first derivative being negative to positive at x equals negative 2 and x equals 3, that must be a minimum. And by the way, notice how his reasons are always about the graph that's given to you. That's very important. That's the expectation in calculus. If I went back to the previous problem, which I'm not going to, all of the reasons included f of x. So let's flip it. If f prime of x changes from positive to negative, then we have a relative max at x equals 1. We can also answer the questions about concavity, because if the first derivative is increasing, that means that the second derivative is positive. Well, if the second derivative is positive, then the function is concave up. Concave down, same reason, just flip it all. If f prime is decreasing, then the second derivative is negative, which means that the function is concave down. And if we ever change concavity, then we have a point of inflection, or you can say that f prime has a relative extrema. So you can say, you don't have to say relative extrema, you can say relative min or max. And really those last couple are all we can say about the second derivative. And if it's helpful, I would strongly encourage you to draw the graph. So you may need to pause or rewind because this is the answer key, and I have faith that you'll figure it out, or you'll come to me and ask questions. So with the third one, really the same thing, except now we're given the second derivative, we have to work backwards. Again, I think it's very useful if you practice, trying to draw things, and and you can shift up and down. So the only thing that you really need to know is that right here, this point needs to be a relative min, because we go from, relative min for the first derivative. I don't know why this is not erasing that point. Let me fix that. And you can shift that up and down as much as you want. Maybe I don't know exactly where. But it has to go like this. And then notice that the second derivative goes from positive to positive. So it's not actually, I'll just make it right here. It's not actually an extrema. It'll look something like that. And then the same thing from there is, depending on what your graph was, you'd have some work to get the original function. So go ahead and write some conclusions. I really can't show you the first derivative unless you actually knew f prime of x. That's kind of an issue that we have. So let me show you the answer key on that. You can hit pause. Write down what you need to. I wish I could probably zoom out and show you more. But anyway, and I will see you in a second video to explain the fourth page of these notes.